Hello there, this is Jude Socrates. Welcome to video number 27 in my video series for multivariable calculus, known as Math 5C at Pasadena City College. So in our video today, we are going to look at a new kind of function, which is called a vector field. So that might sound like vector functions, which we introduced the other day, but this is actually a different kind of animal altogether, right? So we're not going to do any integration today, but we will do some derivatives. So I will see you in a minute on page 221. All right, so here we are. And full disclosure, what we're going to look at today is really most relevant if you're studying physics, right? So in particular, if you're studying gravitation or electricity or magnetism, okay? So we're going to define what are called vector fields. And in physics, they are also known as gravitational fields or electric fields, velocity fields, and magnetic fields, okay? So there are two flavors depending on how many variables you have. So a vector field in 2 dimensions, we'll write it as a capital F, usually boldface, with an arrow on top to indicate that it's a vector function. In 2 variables, x and y, it's a function where the output is also a vector and it has the same number of components as the input. Okay, so you have an x-coordinate and a y-coordinate. Both of them are functions in x and y. Okay, so we have used this notation before. P of xy, q of xy. Those denote functions, scalar functions of 2 variables, right? So that is one number. This is another number. Okay, so basically what it is you input a point xy from some region of the plane, maybe it's all of R2, and you output a vector, which is a vector in R2, right? So in 3 dimensions, we have, of course, an analogous definition. We now have a vector function in x, y, and z, and you have 3 components because you have 3 input variables, okay? So you have p of x, y, z, q of x, y, z, and r of x, y, z. And again, each of these represents one number. Okay, so you have 3 scalar functions assembled together in a vector. Okay, so we're going to look at some pretty pictures, right? And so what that means is we're going to graph these vector functions. Okay, so we're going to start out by making tables of values, and then we'll go to GeoGebra. I'll show you an app that does this for us. All right, so here's a relatively simple vector field. You have f of xy is 2x plus 3y for the first coordinate and x minus 2y for the second coordinate, okay? So here are just random pairs of numbers for x and y. We can plug in any numbers we want because both of these functions are defined for all real numbers. Okay? We're not dividing by 0 or anything weird like that. So if you plug in 0, 0, your output is, oh, that looks like 0, that looks like 0. Okay, how about 3, negative 5? Okay, so we're going to get 6 minus 15. Yep, negative 9. And how about for the second component? 3 plus 10 makes 13. Okay, and so on. Okay, so plug in any 2 numbers that you want, and you'll get a vector for an answer, also represented by 2 numbers. Okay, so I'm going to show you on the internet how to find the 2 apps that we're going to use. All right, so just search on the web. You can use Google, and we will look for GeoGebra and vector field. Okay, so I've obviously looked for it before, and the results will give you these over here. Okay, so these are the 2 apps that we are going to use. All right, let's look at the first one. All right, here we go. So yeah, we don't exactly see GeoGebra. We see what's going on with this app, okay? And you can go full screen if you want. Right, so here we have a vector field. His notation is F1, F2. So this is his login default page. So you have two trig functions, okay? So basically what this says is that if you input, let's say, this point, okay, which is at 1.5.5, okay, the x-coordinate will be sine of 2 radians, okay? And the y-coordinate for that vector, what is the difference? 1.5 sine of cosine of 1 radian, okay? So that is how that vector is going to look like. Okay, so yeah, there are two things we can do with the app. Okay, three things rather. You can zoom in and out, okay? There we go. So as we zoom in, more vectors are being plotted. Okay. Now, of course, if you zoom in too far, yeah, that's not exactly very useful, right? It's like a bunch of sticks that you just dropped and fell to the floor. Okay. All right. As you zoom out, notice that the vectors kind of shorten. Okay. So these are not drawn to scale. Okay. Yeah, let's put in something a little bit more normal, maybe. How about 7x plus 2y? Can we do a square? Yeah, let's try that. And oh, look at that. And how about 3x squared minus 5y? Ooh, boom. Oh my goodness. Whoa. So that, yeah, that looks kind of crazy. Let's lessen, okay, there you go. If you lessen the density, okay, then you see less arrows. Okay, let's try the scale. It'll happen. Ooh, okay, so now they're getting shorter and shorter. Okay, that's about the shortest it gets. All right, so maybe the square is what's making them a little too long, right? Because square numbers, they get big very quickly. Okay, there we go. That looks a little bit more normal. Maybe we can make it more dense. Oh, okay, that's interesting. Can we make it shorter? That's about as short as it gets. Okay, yeah, now, yeah, that doesn't look very pretty now, does it? Okay, there you go. So that is the graph of a two-dimensional vector field. All right, so what we can do in 2 dimensions, you can also do in 3 dimensions. So now you have x, y, and z, and you have 3 functions in this vector. Okay, all of them depending on x, y, or z, or a combination thereof. We can make a table of values, but you already know the idea. So if you plug in 3 minus 2, 4, you'll get 3 plus 8, right? Because that's z, that's 4. So you'll get 11. Y minus z, minus 2 minus 4 minus 6. There you go. Okay. X minus y minus z, 3 plus 2 plus 4. Yeah, so we get 9. Okay, so let's play with the 3-dimensional version. Same author. Okay, let's go back to the web. All right, so let's go to Vector Fields 3D. Okay, there you go. Same author. And yeah, so this time we have 3 components, okay? And he only lets you do one thing, okay? Change the scale, okay? All right, so yeah, we're going to see something that actually looks like this in a few minutes. So what I'm going to do is I am going to turn that into a minus, and I will raise this to a power, and it might look a little strange to you, but that power is going to be 5 over 2. Okay, is that right? Oh, no, just 3 over 2. Okay, there you go. And over here, we will also make this a negative, and same power. Raise to the power 3 over 2. Last one, make that negative. Whoops, not there. Over here. And raise to the power 3 over 2. Okay. Ooh, okay, so there you go. So earlier, the arrows were pointing outwards. Okay, so this time, they're all pointing inwards. Okay, So yeah, let's see if we can increase the scale a little bit. Okay, there you go. So notice, yeah, that the arrows are very short when you're far away from the origin, and they're getting longer as you approach the origin, okay? And that's because, of course, x squared plus y squared plus z squared, that represents the square of a distance, okay? We've seen this in spherical coordinates, for example. That's your rho squared, okay? So rho squared to the 3/2, ooh, that's actually rho cubed, okay? So you have negative x over rho cubed, okay? So yeah, this is going to appear in a few minutes because we're going to look at the gravitational field, okay? So it is defined everywhere except at the origin, because now we're going to be dividing by 0, okay? But the closer you are to the origin, the bigger the number is, okay? Because yeah, when you divide something with something close to 0, you get something very large, okay? So yeah, how about something a little bit more regular, so to speak, like 2x minus 5z. Ooh, wowee. And now how about x plus y plus, whoops, not underline, plus y plus 2z. And last but not least, how about we have 3y minus 4z. Ooh, oh my goodness, what a mess. Okay, so maybe let's reduce the scale. All right, okay, so now it's supposed to get shorter, shorter. Yeah, and I think, no, it doesn't allow us to rotate either. Okay, can make it shorter. Yeah, oh, okay, so there you go. Okay, so now we can maybe appreciate it a little better. Okay, so of course, yeah, these numbers can get really large as x, y, and z get bigger and bigger. Okay, so enough playing. Let's go back to our ebook. All right, so yeah, let's talk about the gravitational force field. Okay, so what physicists do is they idealize a scenario. Okay, so imagine a universe where there's nothing, complete emptiness, except for one planet. Okay, sounds ridiculous. Okay, but it's useful to simplify the calculations. Okay, so we will situate that planet at the origin, 0, 0, 0. Okay, and let's assume it has mass capital M. Okay, so that planet is going to attract other objects. Okay, so what we're going to do is we assume that we have another mass, let's say a ball, of mass exactly 1 kilogram. Okay, and we put it at the point x, y, z. Okay, so that's where the 3 coordinates are going to come in. The location of that point is at x, y, z. Okay, so what is the force that this object experiences? Okay, so first thing we should notice, of course, is that whenever you drop something, it falls down to the ground. It doesn't fly away. Okay, so gravitational force is always attractive, right? So it's always from the mass to the other mass. Okay, it's always pointing, in this case, towards the planet. Okay, how strong is that force? That's the tougher question, and that's where, of course, Sir Isaac Newton comes in, the guy who dropped the apple. Of course, that didn't really happen. So the force, he says, is proportional to the product of the two masses. And because we have 1 kilogram, okay, we only have capital M. But by the proportionality principle, okay, we have a constant here, capital G, which is called the gravitational constant. Okay, we don't have to worry about that value. It's constant, allegedly, which is true everywhere in the universe. More importantly, the strength of the field, okay, in other words, its magnitude, is governed by what's called an inverse square law. Okay, So we mentioned that x squared plus y squared plus z squared, that's the distance squared from the point to the origin. Okay, so we have this inverse square law or principle. Okay, so the magnitude of the force is this essentially constant. It only depends on how heavy the planet is, how massive the planet is, I should say, divided by the square of the distance, x squared plus y squared plus z squared. Okay, but of course, a vector is not just a magnitude, it must have direction, right? So the direction I said is, well, from any point, you just draw the vector to the origin. Okay, so what is that vector? Well, if you're at x, y, z, the vector x, y, z is the vector from the origin to the point. Okay, so if you want to go backwards, you have to get minus x minus y minus z. Okay, so that is the direction of the force. Okay, so put them together. How do you get the actual vector field that represents this force? You multiply the magnitude of the field by the unit vector corresponding to the direction vector. Okay, because if this is a unit vector, okay, so remember the principle, the magnitude of k times v, where k is a constant, is the absolute value of k times the magnitude of v. Okay, so if this is our v, the magnitude is going to be 1, okay, because we have transformed it to a unit vector by dividing by the length. Okay, oh, that's what it is. Okay, so if you multiply these two together, these are actually similar factors. Okay, so that is a power 1, and this is a power 1/2 of x squared plus y squared plus z squared. So that's a final power of 3/2. Okay, so we can of course put that into the vector, but then it's going to look really ugly. Okay, so yeah, if they have the same denominator, even though that's a function of x, y, and z, to be totally transparent, as you can see, it looks cleaner if we just keep it factored outside. All right, so we have been creating vector fields kind of randomly, okay, as we did in the GeoGebra apps that we just saw, okay? And then we had a vector field that comes from an actual physical situation, okay, the gravitational field, okay? Now we're going to look at vector fields that come from a single function, okay? We're going to start with a scalar function, f of xy, or f of xyz. We're going to create what is called the gradient vector of that function, okay? And because of the word vector there, it's going to be a vector field, okay? So the symbol for that is this funny symbol here, which is called the nabla, okay? And it's actually an inverted capital delta, right? You turn it upside down, it looks like delta, okay? So this is pronounced the gradient of f of xy or the gradient of f of xyz. Okay, what's it made of? Ooh, it's a vector where you see the partial derivatives of that function. Okay, so you have fx, fy, or fx, fy, and fz. Okay, so to complete the picture, we will say that capital F of xy is the gradient of little f of xy, and so on for x, y, and z. Okay, so here's an example, but let's go to our workroom, first time today, and make a fresh example. Okay, so this is a little bit longer than what we have in our ebook. Let's find the gradient vector of this function of 3 variables. Okay, of course, it's just a polynomial in x, y, and z. Okay, so I hope you remember how to take partial derivatives. And I do have a ready numbler over there. I just have to put an arrow on top. Woohoo! Okay, so who is the gradient of f of x, y, z? Okay, so I have a vector ready over here for us to fill in. And we'll just erase that and that and that. Okay, so for x, partial x, Okay, so we see a 10xy here. And then we have nothing here, that's going to be 0. And then we're going to get minus 4yz squared. Oops, habit. Nope, I have a different exponent. Way to make an exponent here. Oh, there's a 2x there, so plus 2. Minus 8z goes away. Repeat for y. Okay, so we have 5x squared. I see a 6y in there, 6yz cubed. Anything else? Yep, we have a minus 4xz squared and nothing else. So those go to 0. Z, nothing for the first. For the second, we have 9y squared, z squared. Yeah. Okay, z, we get minus 8xyz. And we get, one last term, minus 8 over there. Okay, so that is our gradient vector, and I'm showing you my menu over here. Whoops, actually, let me go a little bit lower. Haha, because we can check our work. Let me highlight that function. We go compute, woohoo, vector calculus gradient. Okay, am I right? Am I right? This 10xy, 2, that's the x component, 5x squared, 6yz cubed, minus 4xz squared, 9y squared z squared, minus 8xy. All right, everything is good. Okay, so that is the gradient vector of our scalar function. Okay, so we also say that this function is a potential for this vector field, a potential function for this vector field. Okay, so in physics, we have what's called potential energy, and that's really where that word comes from, as we're about to see. Okay, so let me draw your attention first to what we got for the gravitational force field. Okay, so this was our final answer from a few minutes ago. So now we're going to go backwards. Okay, we're going to look for, not exactly, I'm going to give it to you, and in fact it's right there. This function, the scalar function f of x, y, z, is a potential for this vector function. Okay, if we take the gradient of this scalar function, we are going to get the 3 components of this vector field. Okay, where did this come from? We're going to see in a couple of videos. Okay, we're actually going to solve for that, right? But for now, yeah, where did this come from? Okay, so where did this come from? We see a minus x here and an x squared, y squared, z squared to the 3 halves here. Okay, and so we want a function whose derivative is this thing. Its partial derivative with respect to x is this thing. Okay, so after you take the derivative, you're supposed to get this. Okay, so what does that mean? Okay, so you kind of have to take the antiderivative, and that's how we're going to do this in a couple of videos. Okay, so notice when you take a derivative of this thing, okay, chain rule, you need a 2x, okay, and that is where that x is going to come from in the numerator. But where did the 2 go? Okay, so that is where this power of 1/2 comes in. Okay, so if I said, yeah, I'm going to give you a little spot here, a little spot. I'm just going to give you this function. Okay, all you have to do is check that the 3 partial derivatives are correct. Not very satisfying. I mean, you're not 7 years old. Okay, you can do calculus on your own, but it's coming. Okay, so take the partial derivative, this one with respect to y. Okay, so gm constants. Okay, so those can go out. Okay, power rule, 1/2, the whole thing. I'm sorry, it's not 1/2, it's minus 1/2 because it's in the denominator. So drop the minus 1/2 and then take the whole thing, subtract 1. So that becomes minus 3/2. Ooh, that's the 3/2 that we see over there. Chain rule, partial with respect to y, so we need an extra factor of 2y. Okay, guess what? The 2's cancel, but that negative, we need that negative. So you get negative y times this to minus 3/2. And that is exactly the denominator that we get. Positive power to the 3/2. And the negative y, of course, stays inside our vector. Okay, so yeah, I thought it would not be as long as our other vectors. So I hope you enjoyed seeing vector fields for the first time. In our next video, we are going to create integrals which involve these vector fields, contour integrals. Okay, so this will be a new kind of integral. But again, it's important in the field of physics. Okay, there's really not too many other areas where these contour integrals are relevant. So until then, I hope you enjoy the rest of your day, and I will see you in our next video. Bye.